In this video, we are going to look at another implementation of a dictionary using hash tables. The idea is if we can convert a key to an index in constant time, then we can find a keyed element in constant time. If we have a key, we can use a structure such as an order list or binary search tree to find the value with that key in logarithmic times. If we can convert a key to an index in constant time, then we can find a keyed element in constant time. The method. A hash function converts a key to an index. Given an array A, a hash function h, and the value v, we store v in the array A at position h key v. The function h key, which takes a parameter as a key, return an int. The output of this function is in the range 0, length of A excluded. All outputs are equally likely, or at least close to be equally likely. This means that we'll be able to have a key which is equally distributed throughout 0 to length of A. The array hash function pair is called a hash table. Unfortunately, it is impractical for a hash function to be injective, that is, 1-to-1. Consider a hash table indexing by your student number. We will need an array of size 10 to the power of 8, which is 100 millions. That takes too much space in memory. So this to lead to clashes. Two keys k and l clash if hk equals hl, meaning that two different values k and l can lead to the same value via the function hash. There are two ways of dealing with clashes. Either we use separate chaining, also called open hashing, or we can use open addressing, also called closed hashing. We're going to address both of them. But first, let's look at separate chaining. The idea behind this principle is that each cell of the array stores a subdirectory. Any value whose key hashes to index I is stored in a subdirectory at index I. Subdirectories could be implemented in any way. For example, unsorted list, sorted list, binary search tree, or even another hash table. For engineering reasons, subdirectory is always an unordered linked list, hence the name separate chaining. It is also called open hashing because the data is stored outside of the array. A question for yourself is, why is an unordered linked list the best choice? Let's look at an example. For example, we've got 4 key data pairs. The data attached to the key is not shown in this example. And we've got one clash. Here, the hash of A is equal to the hash of D and is equal to 1. For the value B and C, the hash is equal to 3 and 4 respectively. Nothing hashes to 0 or 2. This is recorded by an empty list. This looks like this. So we've got an array of 5 elements. The first element points to an empty list. The second element points to a linked list having 2 elements. The third element points to an empty list. The fourth points to a list which contains only 1 element. And similarly, the fifth element points to a list containing only 1 element, the element C. This is separate chaining. As you remember, we've seen how useful is a linked list, and all the attributes of a linked list will be attached to that data structure. Simple uniform hashing is when the hash function distributes keys evenly. That is, the probability that key is hashed to a particular slot is independent of the keys already in the table. And it is 1 divided by the length of the table. The load factor, A, of a table is the average mean number of items per slot. with n items stored in the table, and L the number of slots, the load factor alpha is equal to n divided by L. Time for an operation is constant for the hashing, plus the time to execute the operation on a list of length alpha. And here we assume a linked list for the subdirectory. If there is an upper bound on the number of elements that can be in the table at any time, operations are in constant time. All operations are in constant time in that case. If there is no upper bound, then operations are, in the worst case, linear. Operations are same asymptotic timing as for corresponding list operation, but applied to a shorter list, and faster by a factor of 1 divided by L on average. But we need to consider the case where all the elements are stored in a single list, meaning we've got a lot of clashing, so every element will be stored in a single list at a given index. In that case, the search, the insert, and the delete will be in logarithmic time. When we want to traverse the entire HashTable, then we have a worst case of n plus L. N the number of elements, and L the number of slots, because we will have to visit every single slot even if that slot is empty. And when we visit a slot with some element, we will have to go through all the elements in that slot, and the n plus L. All data stored in a table is the idea behind the open addressing. There is no external structure. That's why we call it as well closed hashing. In the event of a clash, new item is stored in a different slot, hence open addressing, where the address is a slot. So given an index, given a key, where the HashTable given index, that element may not be stored at this index, but another one. The process of finding an appropriate empty slot or searching past clashes is called probing. Probing identifies a sequence of slots for each keys. The sequence is a permutation of the slot in the table when inserting. When inserting, slots are probed in the order of the sequence until an empty slot is found. Note that we need to have a special value to represent an empty slot as well. If there are no empty slots, then an error occurs. The table is already full. Unlike separate chaining, HashTable, which may grow arbitrarily, open addressing HashTable have a maximum number of entries. Several probing strategies to generate sequence include linear probing, quadratic probing, and double hashing. But for this lecture, we'll be looking at linear probing only. For the rest, you can read the different chapters provided at the end of the lecture. Choosing a strategy balances simplicity with effectiveness. Linear probing is simple, but not effective. Double hashing is effective, but not very simple to implement. Let's have a look. Linear problem is a simple strategy, but it has some problem. The EF slot in the sequence for key k is hk plus I modulo L, the number of slots. Starting with I equals 0, this is equal to starting at hk. And then trying subsequent slot, wrapping around. Example, if the number of slots L is equal to 5 and hk is equal to 3, the sequence of slots to try is first 3, and if it's already occupied, we look at 4. If it's already occupied, we look at 0. If it's already occupied, we look at 1, and so on up to 2. Let's look at this example on the table given below. We've got 5 elements here. And here, hk is equal to k modulo 5. We want to enter the data with keys 19, 71, 6, 3, and 22. So we need to compute the hash key for 19, 71, 6, 3, and 22. And they are given over here. So the hash value for the key 19 is 4. The hash value for the key 71 is 1, and so on. So let's insert the value associated with the key 19. The hash value is 4, so we insert 19 at position 4. Then we look at 71. The hash value is 1, so we insert 71 at position 1. Now we look at hash 6. And here we've got a clash. We've got 1, but 1 is also the hash value for the key 71. So first we're going to try to add 6 at position 1, but it's already occupied, so we cannot put it here. So we're going to look at the next index. So we're going to look at 2. It is empty, so we can add 6 at this position. Let's look at edge of 3. The key is 3, and the hash value associated to that key is 3 as well. So we insert directly 3 at this position. We've got no issue. Now we've got hash for the key 22, which is 2. So there is no clash with the previous value we computed. So we can assume it will be very easy to add that to my hash table. However, when I'm looking at position 2, it is already occupied. So what I need to do is to move to the next index, which is also occupied. And then I move to the next index, which is also occupied. So I need to wrap around and look at the next index starting from the beginning. At position 0, there is no value, so I can insert 22 over here. At that stage now, my hash table is full, which means I cannot add more elements unless I'm doing something extra. But that's something we're going to discuss later on. Now let's look at another issue here. Let's consider deleting datum with key 3 from the previous example. So we look at the hash value for the key 3, which is 3. We find that element, which is equal to 3, so we can delete that element. So now what we want to do, we want to find if we've got datum with key 22. So we try to find the key 22 in that hash table. We look at the key hash value for the key 22, which is 2, and 71, which is not equal to 22. So we continue our probing. So we look at the next element, 6, which is not equal to 22. So that means we don't have 22, but we need to look at the next element because we are keeping the probing. We arrive at this position. This position is empty. Therefore, it means that 22 is not part of my hash table. But as you can see, I've got 22 at position 0. So it does exist in my hash table. So we've got an issue here. So when I delete an element, problem may occur. So we need to find a solution for that. What we want to do is to have a third state for my hash table. Empty is the initial one, so we know we can put an element here. Full, that means that I've got already a value in that slot. And then I've got a ghost value, saying that there is no value over here, but it's not empty. So I will have to continue probing if I search an element. So let's see how it works here. When deleting a cell, the cell is not emptied like I've done in the previous example, but it will be turned into a ghost. Now, when I want to search for the value 22, I will arrive first at position 1. It's going to give me 71. So I keep probing. So I'm going to look at position 2. It's going to give me 6. So I keep probing, and then I arrive at the ghost value. And here, when I arrive at the ghost values, that means keep probing. So now I'm going to move to 19, which is not equal to 22. So I'm going to probe and go back to the beginning, and then I'm going to be able to find 22. So when I'm going to find an empty cell, that means that element doesn't exist. If I find a ghost value, that means keep probing. This technique applies to all collision resolution strategy, not just for linear probing. It will apply for quadratic probing and double hashing too. Linear probing is a simple but suffer from primary clustering. That is, field portion of the table tend to grow very quickly. Consider the table presented here. There is a 70% chance that one of the slots, 3 to 9, will be the initial probe of the next insertion, causing the segment to grow. Even worse, there is almost 60% chance that 2 inserts will both cause the cluster to grow. If both of these cause growth to the left, that's around 42% chance, the cluster will emerge with the value in slot 1 to form a cluster of size 8. Because of primary clustering, search in linear probing HashTable quickly drops from constant time to linear time. And that's an issue we need to resolve. Quadratic probing will avoid primary cluster, but unfortunately does suffer from secondary cluster. However, it will be more efficient than linear probing. Another thing we can do is double hashing. It avoids primary and secondary cluster by using 2 hash functions to generate the sequence of probe. It is more complex as a badly designed hash function will generate a sequence of probes that is not a permutation of all slots, meaning that some of the slots will never be occupied. The complexity analysis of open addressing HTable is very complex to analyze precisely. An average case complexity is close to constant for search and for insert and delete. However, as the load factor increases, complexity increases as well. For a table with 90% occupancy, average number of probes is around 10. So what can we do when we start to have a larger occupancy? We can do rehashing, which is a solution to the problem of an open addressing table filling up. To rehash, we're going to allocate a larger table. Then we choose a new hash function for that given table. We're going to copy all elements from the old to the new table, and finally dispose of the old table. This exercise is ghost, so I'm going to remove all the ghosts in that case. On average, a linear operation if new table is sufficiently large. But thereafter, operations are on average constant until the new table starts to fill up again. Amortized analysis tells us that this is not too bad. So this is a very good solution when a table starts to fill up and we are using open addressing. So we've seen now that to implement a dictionary, we've got different ways of doing it. We can use unsorted array, unsorted list, AVL, and hash tables. We can see that using AVL is pretty efficient. We've got everything in log n. However, a well-designed hash table will be, in general, of constant time, where alpha is the load factor, which is the number of elements divided by the number of slots. But insert and delete in a well-balanced hash table will be constant. It should be noted that log n is guaranteed for AVL, whereas constant time is not for hash tables. Depending on table occupancy, the load factor, it may become linear. So at the end of this week, you should know what a binary search tree is. You should be able to implement dictionary operation on a binary search tree. You should be also able to maintain balance using AVL trees. An AVL tree or other balance scheme give logarithmic time for main dictionary operation. You should know that we can convert keys into index for storage in HTables. Depending on condition, it is going to give a constant time, amortized, for main dictionary operation. although the worst case is linear time all the time. So we need to be very careful when we make that implementation. To know a little bit more, I recommend to read chapter 4 and 7 of the Melon book, or section 3.3, 3.4, and 3.7 of the Skinner book.